Hey everybody, we're on lecture 3 now for MME 2305, Material Energy Balances. I'm your host, D.A. Robertson, PhD, and I can be reached at that email down there should you have any questions. This lecture is meant to go hand in hand with the 4 basic skills lectures and, the 4 basic skills lectures. And if you haven't watched them, I suggest you watch them either right before this or right after this, but watch them in relatively the same amount of time, preferably before you start trying to work out the problems. And so this is kind of the same subject matter that we've talked about the last 2 sets of lectures. So last week's lecture and then the 4 basic skills lecture. We're going to talk about density again. Specific gravity, which flows in the density, and you saw a way to measure specific gravity in the last lecture, lecture 2. We're going to talk about flow rates because flow rates become very, very important in the solving of material balance problems. We're going to talk about the meaning of G-mole or gram mole as this abbreviates, and we're going to talk a little bit about compositions in this lecture. And again, this is meant to go hand in hand with the so-called basic skills lectures I've put together. And even if you've seen this stuff before, I implore you, watch it again because it never hurts to get a refresher. So we're talking about density and volume and specific gravity. And I put silver as an example, so we'll talk about that here in a little bit. Silver is my favorite metal, if you guys do not know. So density is mass over volume. Specific volume is volume over mass, which is kind of interesting. Either can be used as a conversion factor, excuse me. Specific volume is density to the -1, as you may have guessed, looking at how the units flipped. Specific gravity, so SG, we talked about specific gravity. We actually measured it in lecture number 2. It's the density versus a reference density. So it's the density of your substance over a reference density. I'll say it verbally and we'll go over some examples here in a second. But if you want the density of your material, it is the specific gravity value multiplied by the density of water. And the reference density is typically water at a specific condition. Good old H2O if you're a Waterboy fan. And it's kind of it makes things easier to do calculations, and it'll become more apparent later. But the notation is typically SG equals 0.6, and it has this 20 degrees, 4 degrees. So it's typically the density of your specimen at 20 degrees and the density of water at 4 degrees, okay? And so we have this nice table that came, I believe, right out of the Felder and Rousseau book. So the density of water at 4 degrees centigrade, but in different units. And so this is the trick here, okay? It saves you conversions if you start working in kilograms and you start working in pounds. And it's always pounds mass because there's also pounds force as well. But the density of water, we know this, is 1 gram per centimeters cubed. That translates into 1,000 kilograms per cubic meter, which becomes important when we're doing calculations of bigger quantities. And also 62.43 pounds mass per cubic foot. So we're going to take a look at silver as an example just for density. And we've worked out some density problems already, but we'll do it again. We'll work out, we'll look at zinc here as an example, and we will do this in here in a couple of seconds, and we'll kind of see the difference between using specific gravity and using just straight up density. And we'll take a look at that right now. All right, so just a kind of a simple example. We talked about silver, and the density is 10.5 grams per centimeters cubed. The specific volume here is just the inverse. So I got 0.095 centimeters cubed per gram. And we've kind of seen some of this stuff before where we want to calculate some stuff and, you know, what volume will, let's say, you know, 100 grams. What volume will 100 grams of silver occupy? And I'm going to do that. Then we're going to kind of do a flow rate, and we'll do kind of an example of in silver. I guess, you know, we're lucky if we're having silver flowing. So what volume will 100 grams of silver occupy? And we could do it two ways. So we could actually use a specific volume, since we've seen examples of using density. And so there are 0.095 centimeters cubed per gram. And kind of just using silver to kind of keep the placeholder. And I probably should have started with 100 grams of silver, which is the better convention. And so grams of silver cancels out. So 0.095 times 100. And that's 9.5 cubic centimeters. All right, so now we can kind of take a look at we can use density to convert this time if we want. Well, let's just see how it plays out. So we have this problem in a coin factory. Silver flows, I probably should have a comma. Silver flows with a mass rate of 150 grams per minute, and this should be mass flow rate. Mass flow rate of 150 grams per minute. What is the volumetric flow rate of silver? And so we have what we know. It's good to start writing out what you know. So we can even kind of subscript Ag for argentum or silver. So the mass flow rate of silver is 150 grams per minute. And we want to know what the volumetric flow rate is. So is what? So we don't know. And so we can start off with 150 grams per minute. And we can look at what we have. So we have our specific gravity and our specific volume and our specific gravity. And mathematically it works out the same. We have our density and we have our specific volume. And so it kind of works out the same. So let's just go ahead and use density. So 10.5 grams per centimeters cubed. So we're using density now to be a conversion factor for a mass flow rate. And so grams cancels again. And so now we're going to end up with centimeters cubed per minute. So we'll get our volumetric flow rate. So 150 divided by 10.5 is 14.28. per gram. Let's do it again using specific volume. So again, but using specific volume. So again, we start with 150 grams per minute. And we have a specific volume this time. Mathematically, it's the same. So 0.095 centimeters cubed per gram. And so 0.095. And again, grams cancels. Mathematically, dividing it by 10.5 is the same by multiplying it by 0.095. You might be off a little bit because I rounded somewhere, but... And I got 14.25, so I'm a little off because of rounding, but it's pretty close. And it's all about keeping the units in check. And so we've seen specific volume. We're going to see specific gravity in a little bit. But we've seen specific volume and density both used as a conversion factor to convert between mass flow rate and volumetric flow rate. And so that's pretty much all there is to it. All right, so now we have a specific gravity problem. So we said we we're going to use zinc as an example. And so the specific gravity of zinc here is 7.1. And so if zinc is 20 degrees and water is 4 degrees centigrade, so that's kind of the standard. And so we have this little problem we kind of made up based on the specific gravity of zinc. What is the volumetric flow rate of zinc in cubic meters if 2,500 kilograms per hour of zinc is processed in a battery factory? And so instead of using density, which would generally be given in terms of grams per centimeters cubed, we're given the specific gravity of zinc. And the freedom that gives us is it allows us to kind of save from doing extra conversions. And so we were given the density of water on the slide, different flavors. So density of water is of course 1 gram per centimeter cubed. It's also 1,000 kilograms per meters cubed, and it's also 62.43 pounds mass per cubic foot. And maybe I should have done this in English units, but let's go ahead and do it with kilograms. And so the freedom this gives us is we can basically figure out the density of zinc in whatever unit we want. Okay, so it's a little shortcut. And so 7.1, and then we have to multiply it by our density converter. And if you analyze the problem, we're looking at kilograms and we're interested in cubic meters. And so it's easier to work with this particular version of the density of water. So 7.1 times 1,000 per cubic meter. And so that's going to equal, I always use a calculator even if it's simple, maybe I shouldn't, but 7,100. And so now we have an easy way to convert it. So we want to know what the volumetric flow rate of zinc is. And again, it's kind of similar to the problem we did with silver. And so the mass flow rate of zinc is equal to 2,500 kilograms per hour. And so we want to know what the volumetric flow rate is. So what's that equal to, huh? So we can start off with 2,500 kilograms per hour. And then we've already made our conversion factor. So in this case, we're making a conversion factor out of specific gravity. And so 7,100, always keep the units straight and you'll be okay. The units in these problems tend to force you to work them out right. So it's almost impossible to get it wrong, but you got to pay attention to the units. That's the number one thing I can say. So kilograms cancel. We're going to get cubic meters per hour, which is what we're asked for. And so 2,500 divided by 7,100, and that's equal to 0.3521 cubic meters per hour. Kind of a small number, but that's all there is to that. All right, moving on to chemical composition. I said earlier, I believe in lecture 2, that when you look at the periodic table, the atomic weight, or sorry, atomic weight, excuse me, atomic weight is kind of understood to be grams per mole. And you can basically change that a little bit. And you can say other units of mass, basically. But you have to change what type of mole you're talking about, okay? And I'll try to work through a quick example and to try to make it a little more clear than my jumbling words. And I'm trying to get my laser pointer so I can laser pointer it up. This is right off of a periodic table. So aluminum 26.98 grams per mole. If you say, if you can talk in terms of other types of moles, okay? So generally, if we say mole, we mean a gram mole. We can specify kilogram mole, okay? But then you have to change your unit of mass. So 1 gram mole of alumina, and I got this number by basically multiplying 27 times 2 and adding it to 16 times 2 to get 102 grams. So 1 gram mole of alumina weighs 102 grams. 1 kilogram mole of alumina weighs 102 kilograms. And 1 pound mass mole of alumina weighs 102 pounds mass. Okay. So generally it's understood when you say mole, you mean a gram mole, but you can also work in different flavors of moles. So kilogram mole and pound mass mole would be two other flavors of moles that we work with. And let's go ahead and take a look at an example and kind of do a little bit of conversion so you can kind of see how the magic happens and why you actually want to use different types of moles in some of these calculations. All right, so we're looking at this problem involving kilogram moles and then also gram moles, so you can kind of see where the conversions kind of occur. And so we want to know how many moles of aluminum is in 3,500 kilograms of alumina. And so alumina is Al2O3. And so we got to do some kind of chemistry type of stuff here. So we have 3,500. So it's okay to start. This is our basis. We don't assume a basis here, but we have a basis. And I've kind of not verbally said it in some of these examples. And if I haven't, I apologize. And let me make this here. So 3,500 kilograms of alumina, sorry. And we want to know how many kilogram moles there are. And so we're starting off in kilograms, so we can keep it all in terms of kilogram moles. And there's a 2 to 1 ratio here. And so let's do our Al2O3. So our Al2O3, we know there's 102 kilograms in Al2O3 in 1 kilogram mole Al2O3 or alumina. Okay, and based on this chemical equation, or not chemical equation, chemical formula, if you will, we know the relationship between number of moles of aluminum and number of moles of aluminous, because we're looking for aluminum in this case. And so there are, for 1 kilogram mole of alumina, there's 1 kilogram mole, oops, I messed up. There's 2, because it's Al2O3. So 2 kilogram moles of aluminum. Okay, you all see that hopefully. And so do our units cancel? This is why you want to start getting in the habit of labeling everything. So kilograms Al2O3, and you know what? Let me cancel it with a different color. Kilograms Al2O3, kilograms Al2O3, kilogram moles Al2O3, kilogram moles Al2O3. And so we're going to get kilogram moles of aluminum at the end of the day. And so we've canceled. We can use our calculator. So there's 3,500 divided by 102, and we want to multiply that by 2. And so the answer now is 68 I'll round 63, and work along with me and see if you get the same answer. If you don't, you can email me. 68.63 kilogram moles of aluminum. Okay, and that's what we were looking for. So this is our answer. Now we're in kilogram moles. We're not in gram moles. We're in kilogram moles, and that was the first part that we were being asked for. So sorry, how many kilogram moles are there? And it's okay to leave your answer in kilogram moles. But now we have a second problem. So I should have done A and B, but it's actually 2 problems. So we want to know how many gram moles now. And so that's pretty straightforward. So we have 68 scroll over, 63 kilogram of aluminum, and we know that the conversion factor is the same. So there are 1,000 gram moles in 1 kilogram mole of aluminum. Okay, so kilogram moles of aluminum is going to cancel. We see our 1,000 factor between grams and kilograms, so it kind of makes sense. And so 68.63 times 1,000. And so that's 68, as you may have guessed. 630 gram moles of aluminum. Let's do what about pound moles? And I'm gonna do a conversion. We'll get our conversion factor. Hear me type it. Oops. All right, so we can do a conversion, and so let's start off with where we ended here. So we have there's 68, 630 of aluminum, and we want to get to pound moles of aluminum. And there are 453.6. So it's just a conversion from grams to pounds. In one alumina. And so I'm going to just divide that by 453.6, and I got 151.3. So I always like to circle my answer. And so when you go between gram moles, kilogram moles, and pound moles, you really just use the conversion between pounds, kilograms, and grams. And that's really all there is to it. But it helps you solve things a little faster, because if you're looking for kilogram moles, well, you can just do things in terms of kilogram moles. And again, always let the what you're being asked, and also always let the units dictate how you work things out. Just kind of reiterating what's been said in the kind of the 4 basic skills videos talking about mass fraction and mole fraction. Both are ratios of the amount of a constituent over the total amount of the substance. So mass fraction is the mass of whatever you're trying to look for over your total mass. Same goes for moles. Same goes for volume, for that matter. Conversion of mass composition to a molar composition can be best done in a tabularized form. And we'll take a quick look at an example of how you might want to tabularize it. So if we look at this exhaust gas, it has the following composition by mass. So it's 16% O2, 4% CO, 17% CO2, and 63% N2. And this probably occurred by the combustion of natural gas, actually, and we'll see that a little bit more detail later. So what would you need to know to figure out the mass of each? Well, you'd probably have to figure out a basis, or be given something that gives you the initial input of the material. So what would you need to know if you're asked to determine the mole fraction of each? Okay, well, it gets a little bit more complex, does it not? So it kind of starts helping to tabularize everything. What would you need to determine the number of moles of each? Again, probably start off with a basis and calculate it through, but it's good to start tabularizing everything, and I'll show you an example table. What would you need to determine the molecular weight of each? That one's pretty straightforward. The molecular weight would be figured out by looking at a periodic table, really. What about volume fractions? That's another thing. You'd have to know the density, and that might not be that straightforward if given what we know about the effect of temperature on density, because we don't really know the temperature, but we'd have to be given the density at the conditions, and that's very, very important to kind of keep in mind. And so volume fraction would be the volume of the individual gas, whether it's O2 over the total volume of your gases. Here's an example. The table didn't really consider volume fraction, and we'll probably work through a problem that gives you volume fraction pretty soon. But they tabularized it, and it's very important to kind of start getting in the habit of keeping all your species and everything in these problems kind of organized. And so here they've organized the constituents, I guess, of your gas, for lack of a better term. So mass fraction, it was pretty simple. You could get it by multiplying these percentages by, or dividing, excuse me, by 100. So 0.16, 0.04, 0.17, 63. They assumed a basis. So they assumed a basis of 100 grams. Okay. And so 16 grams of O2, 4 grams of CO, 17 grams of CO2, and 63 grams of N2. So again, assuming a basis becomes very, very important. Molecular weight of each of these constituents, periodic table. Number of moles is calculated this way. So you could actually take your mass and divide it by your molecular weight, and you'd end up with moles, and you can work that out. Your grams would cancel, basically. So you end up with moles. And then mole fraction, you have your total number of moles here. So that would just be each of these constituents divided by your total moles. And so mole fraction of this is 0.5 divided by 3.279. And you can pause it here and work it out if you don't believe me. Let's take a look at another example back here. I kind of skipped, and I apologize for skipping it. So mole fraction, mass fraction, and we have other examples in the other skills videos, but let's just do another one. So hydrogen bromide is a chemical commonly used in semiconductor fabrication. What is the mass and mole fraction of bromine in hydrogen bromide? And kind of the key thing is assuming a basis, and so we'll assume a basis again, and hopefully by the time you've finished watching the basic skills videos in this, you'll be pro at assuming a basis. So let's take a look at this example right now. All right, so this is our final example. We're looking at hydrogen bromide, HBr, and we want to know what the mass and mole fraction are of each. So we want to know MI, and we want to know, well, I'm using different terms. So if I didn't mention it before, mass fraction generally, it depends on the text, is either MI or XI generally, okay? And then mole fraction is generally NI or YI, actually. And I tend to like M for mass and N for mole. It makes sense. And so I know there's different notations in some of these lectures, and I apologize for that. I'm a victim of my own experience, and so I've done it both ways in my life. So hydrogen bromide, hydrogen is 1 gram per mole, and bromine is 80 grams per mole. And the molecular weight of HBr is 80 grams per mole. I'm sorry, 81, because it's 80 plus 1, 81 grams per mole. And I probably should be writing it a little bit more sensical. So let me at least fix it here, because I got off of I'll fix it on all of them. I'm sorry. Oopsie. All right, so grams over moles tends to make it easier. So we want to know what the mass and mole fraction is. And let's figure it out. Let me think about it. Always think things through. Probably should do that when we are not on pause. All right, so we need to take a basis. And it's always good to take a basis of a nice big round number. And I tend to use 100 or 1. I don't ever use decimal points for basis. And the reason for that is people tend to make order of magnitude errors. And by order of magnitude, I mean an answer that's wrong by a power of 10. And so our basis is 100 grams of HBr. And so let's kind of figure this out. And so we have 100 grams. And we already said that there are 81 grams in 1 mole. So there's 81 grams in 1 mole of HBr. So we're going to figure out mole fraction first, because that's just kind of how I worked it out. And so grams of HBr is going to cancel. So we're going to left with moles of HBr. And so 100 divided by 81. And so, wow, 1, 2, 3, 4, 5, 6, 7. That's crazy. So I'm going to round and get and work it out with me. That equals to 1.23 moles of HBr. And so we want to get our mole fraction now. So we want to figure out how many moles of each to get to the mole fraction. So we have 1.23 moles of HBr. And so this is our new basis. All right. And in 1 mole, there are 1 mole of bromine. And so that equals to 1.23 mole of bromine. And we're going to do kind of the same, and it's going to be the same for hydrogen. 1.23, but pay attention to the technique. And 1. And this is equal to 1.23 mole of H. And so total moles equals 1.23 for H and plus 1.23 for the Br. And that is 2.46. And it's going to end up being 0.5 if it's not obvious. But the N, and we want to know the N of bromine, right? Because we just want to know the mass and mole fraction of bromine. So N Br equals 1.23 for bromine over the total, which is 2.46. So it's half. So 0.5. Now we want to know the MBr. And we can start off with the same basis. So 1.23 moles of HBr and 1 mole is 1 mole of hydrogen bromide. There's 1 mole of bromine in that. And I'm kind of working it out a little, maybe a little too much, but 1 mole of bromine is 80 grams. According to our basis. And 1.23 times 80 should equal 98. Oops. 98. So I got 98.4. So there's 98.4 grams of bromine. So remember, our basis that we took was 100 grams of HBr. Okay, so that's our total mass. And so Mi equals 98 over 100 grams in total. And so our X of bromine is 98.4 divided by 100 is 0.984. Or 98.4. So does this make sense? Okay, so we said earlier, you always ask yourself if this answer makes sense. And yeah, it kind of does. So by mass, we have two constituents, and we have hydrogen, which is the lightest of all the elements, right? And we have bromine, which is a little bit more, right? So 1 gram per mole for hydrogen, 80 grams per mole for bromine. So does it make sense that a gas, if you will, that's composed of hydrogen and bromine would be mostly bromine in terms of mass? Yes, it does. And so that's all there is to that. And so thank you for looking at this. Please go watch, if you didn't watch them first, go watch the 4 basic skills videos. And if you have any questions, feel free to contact me. Oh my. It's the end of the lecture. If you have any questions, you can email me at drobertson@utep.edu.